I'm here. I'm looking for some markers and something to erase with. That's all. Oops. All right, so I know it's probably not going to be too many people that may be in here or may not. So I'm going to do the best that I can do. I'm going to go from basically the setup of PowerPoint and this whiteboard. So I'm going to do the best I can with what I got to work with. Make this. All right, this pretty good. All right, so again, I know we started with 11.1 in the 1 o'clock class before we left, and we're going to be talking about the fundamental counting principles and permutations. So we are going to use the fundamental counting principle, calculate the value of factorial expressions, find the number of permutations of n objects, find the number of permutation of n objects taken r at a time, and find the number of permutations when some objects are alike. So these are going to be our objectives. Now remember, all of this is on Blackboard still to the day of the last day of class. It's still on Blackboard. I was getting a reflection. Sorry, oops, whatever. Fundamental counting principle and a sequence of n objects in which the first event can occur in K1 ways, the second event can occur in K2 ways, and the third event can occur in K3 ways, and so on. So the total number of ways the sequence can occur is going to be K1 times K2 times K3, and it can go up to whatever number of categories you are working with. And that's why at the end you see Kn, because remember, n is going to be any natural number. That means n can be 100, 1,000, 1 million. But between every step that you see here, you notice that there's a multiplication sign in between. So that means when you're working with whatever numbers, categories we're working with, you are going to multiply when using the fundamental counting principle. All right, so this is going to be the first example. It says there are 4 blood types, A, B, AB, and O. Blood is also either Rh positive or Rh negative. If a local blood bank labels donations according to type, Rh factor, and gender of the donor, how many different ways can a blood sample be labeled? Okay, so just like before, and I'm going to try to hold this camera, I'm sorry, and draw on this whiteboard. But just like before, we just saw the K1 times K2 times K3 and so forth. In this case, they told us we're working with A, B, AB, and O. So these are the 4 blood types that we're working with. So now we're going to make them positive and negative, positive, negative. Because AB is also together as one as a blood type. Positive, negative, and O. Sorry, positive, negative. Now remember, so this is category 1. That could be K1. This is category 2, which is going to be the RH factor, which is positive and negative for each one. And now for this third row is going to be the gender, which is male or female for each one. Male, female, male, female, male, female, male, female, male, female, male, female. All right, so the one thing I want you to pay attention to is we have the first row, which is going to be the blood type, and we have 4 blood types, which is K1, and now we need to put our multiplication sign there. K2 is RH factor, which is positive or negative. So that's 2, positive, 1, 2, negative, positive, negative, 2. Third one is gender, K3, which is 2, because we have 2 genders, male or female. So now we have 4 times 2 times 2, which is 16. So we should have a total of 16 outcomes, means 16 results. And if you want to make sure that you have that right amount of outcomes, let's count them. A positive male, that's 1. A positive female, that's 2. A negative male, that's 3. A negative female, that's 4. B positive male, that's 5. B positive female, that's 6. B negative male, that's 7. B negative female, that's 8. AB positive male, 9. AB positive female, 10. AB negative male, 11. AB negative female, 12. O positive male, 13. O positive female, 14. O negative male, 15. And O negative female, that's 16. So 4 times 2 times 2 is 16. Now when we work with the fundamental counting principle, we are basically going to take the numbers, the category, and multiply them. But I am showing you here that if there's something as simple as one like this that you can actually, write out, you can, in order to see if it's correct or incorrect. Now, when you go to the slideshow on Blackboard, you should also see that they only really give you the 4 possibilities for the blood type, the 2 for the RH factor, and the 2 for the gender. So 4 times 2 times 2 is 16. Now, if you're on here right now, you have a question, feel free to ask the question before we go to the next example if you want to. I know this is different. I know. But at least if we're doing it like this, we have the opportunity for some people to ask some questions. All right, so I don't necessarily see any questions. So let's go to example 2. Example 2, we're still using the fundamental counting principle, but we're using it with repetition. Now, this problem says the letters A, B, C, D, and E are to be used in a 4-letter ID card. How many different cards are possible if the letters are allowed to be repeated? How many cards are possible if each letter can only be repeated once? So we have 2 things that we're going to try to do here today. So give me 1 second so I can erase this board. Hold on 1 second. Hold on, let me flip it towards me so it won't just look blank. Hey, y'all. Well, hold on. I'm struggling, y'all. This board is not like the big one in class. Okay. So we're back to our problem. Let's just do a card. Let's make our own ID card if I can open a marker. Okay, so with our ID card, got a little person in the corner. Remember they told us it's a 4-letter card. And we can use the letters A, B, C, D, or E. Alright, so on the first one, it said how many different cards are possible if letters are allowed to be repeated. Alright, so that means in this case, for this first spot, we have 1, 2, 3, 4, 5 letters. If we have 5 letters, that means that 5 letters can go here. Now remember, it says that the letters are allowed to be repeated. So it does not matter if we use A, B, C, D, E, F, or G. Well, you know what I'm saying. That means there's still going to be 5 letters still available for this spot, and that spot. So that's only if the letters or the object that you're working with are able to be repeated. So technically, this gives us 5 to the 4th power. So that's 5 times 5 times 5 times 5. 5 times 5 is 25 times 5, which is 125, times 5, which is 625. So if we had a ID card and we had the opportunity to repeat any of the letters for those 4 slots, we would have 5 times 5 times 5 times 5, which is 625. Now we see that the second part says how many cards are possible if each letter can only be used once. Now when we come to this card and we have our same 4 slots, we have to work a little different. And the reason why we have to work a little different, if they cannot be repeated, we have 5 letters. So that means for that first spot, we have a possibility of putting any one of these 5 letters here. So if we use B, now B is gone because B has been used. So that means for spot number 2, I only have 1, 2, 3, 4 letters. If I use C, now C is gone. So I only have 3 letters left for the third slot. If I use A and A is gone, I only have 2 slots left for the 2 letters left for the last spot. If I use E for the last spot, then we've used all 4 letters. So now we have 5 times 4 times 3 times 2. So 5 times 4 is 20, times 3 is 60, times 2 is 120. So that means if we had a ID card with 4 slots for letters, and we can repeat letters A, B, C, D, or E, we have 625 ways that you can write that ID card. But if we have a card where we have the same letters, A, B, C, D, and E, that cannot be repeated, then that means that we have 120 ways that we can write that ID card. Let's see if we were right. It looks similar to me. All right, if y'all have any questions, just like before, feel free to ask them now. And I'm going to plug up my computer while if you are typing a question. If not, give me like 30 seconds. I'm still here, just need to plug up my computer. Now where's the plug? Yes, RH is it's more of a category because remember RH is a factor of blood is either positive or negative. So when we had the RH factor, that was two different ones, which was positive and negative. So that was the category. You had three categories. One category was the blood type, which was 4, which is A, B, and O. The RH factor, which was positive and negative, which was 2. And then you had your genders, which was male and females, which was 2. So 4 times 2 times 2 is 16. All right, so next we're going to talk about factorial notation. And factorial notation, I don't know if you guys have ever seen an exclamation point after a number, but that's what we call factorial, is the exclamation point. So here you notice it says for any natural number n, we can categorize it as n factorial, where n is equal to n times n minus 1 times n minus 2 times n minus 3, and so forth. And your answers should always come out being descending, like 3 times 2 times 1. Once again, like I said, n factorial, or n with an exclamation point, is read as n factorial. So let me show you an example that kind of justifies the n exclamation point into that equation. All right, so if we have, let's just use a number here. We're going to use the number 3 because this board is not that big. So we use the number 3 for that n factorial. So let me write that first. N factorial was n is equal to n minus 1, n minus 2, n minus 3, and I'm just going to put so forth past there. All right, so let's actually use 3 for n. So it's going to be 3 factorial versus n factorial, which is nothing, because you remember n is any natural number. So 3 is the natural number that we are using. So here we're going to have 3 for n, 3 minus 1, 3 minus 2. And pretty much we can't do 3 minus 3, because one thing with factorials and factorial notation is you cannot multiply by 0. We all know that anything times 0 is itself. So the point or the goal that we are trying to accomplish here is counting down from whatever number is n. And in this case, it's 3, all the way down descending to 1. Because now, when I work it out, I'll have 3 staying the same. 3 minus 1, which is times 2. 3 minus 2, which is times 1. We do our math. 3 times 2 times 1 is simply 6. So one of the key things to remember with working with factorials is going to be that you have the ability to simply see the number you're starting with and basically multiply it down to the number 1. I know you guys remember in algebra seeing x to the 0 power. And we know that x to the 0 power is 1. So with factorials, 0 factorial is going to be defined as 1. Anything to the 0 power or 0 factorial is going to be characterized as 1. The reason why I'm telling you that is because remember, anything times 0 is 0. And we do not want the answer to be 0 because we want to get an answer. So here at the bottom, it simply just says the symbol for a factorial is the exclamation mark. In general, n factorial means to multiply the whole numbers from n down to 1. Basically, like I said, make sure whenever you're working with any number that is n, it is always going to descend down to the number 1. So if you want to use the formula, you can. But just know that if you had 8 factorial, it's going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If it was 12 factorial, 12 times 11 times 10 times 9 times 8 and so forth. So that means even if we got up to 100 or 1,000, it's always going to be every single number from the number n descending down to 1. So here are a couple examples that are at the bottom. If we were talking about 1 factorial, then it would simply just be 1. And 1 is equal to 1. If we have 2 factorial, 2 factorial breaks down to 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, which is 6. And 4 factorial, which is 4 times 3 times 2 times 1, which is 24 when we multiply. Now, one thing that I like to use or say in my class is make sure that you understand when you see this number and the factorial sign, that makes that number not the regular 3. That factorial makes these factorials, or the exclamation point next to the number, makes it like a package deal. We know that if we go to the store and we buy candy, let's say we go to the store and we buy a pack of Skittles, we know that what's inside. Numerous Skittles, the candy, are inside of a bag of Skittles. So when you see this factorial, you can look at it as a can of Skittles, a package of Skittles that has Skittles inside, which will be the numbers that descend down to 1. I even have used the analogy of corn. If you get a can of corn, you have kernels of corn in it. So anytime you see the number and that factorial sign, just know it's not the regular number 3 or the regular number 4. It's literally that number descending down to 1 because it's the factorial notation of the number. All right, so here we are getting more into actually dividing our factorial notations. So some of the formulas we'll be working with require division of factorials. This will be simple if we make 2 key observations. Just like the Skittle analogy, it's the same thing here. If you see n factorial over n factorial, we always know that whatever the number is going to be 1. The reason why is if we had 3 factorial over 3 factorial, when you open your package and break it down, 3 times 2 times 1 for the numerator and 3 times 2 times 1 for the denominator, then we have 6 over 6. And 6 over 6 is still going to be 1. Now make sure that you remember, but just make an observation of this, if nothing else. When you just notice that if we did 3 over 3, we know that's 1 because why? The numbers are 3 and 3 and they cancel out. But if we have 3 factorial over 3 factorial, that breaks down to 3 times 2 times 1 over 3 times 2 times 1, which once again, they can simply cancel out to 1 and 1, 1 and 1, and it's still going to be 1. But as they did it here, instead of canceling out in this portion right here, they did 6 over 6 multiplying, which is still 6 divided by 6, which is 1. All right, another key factor to make this a little bit simpler for you when you go forth and start working on these is going to be to know that you can write the formulas without writing all of the factors down to 1. And the examples at the bottom are giving you 5 factorial, which we know is 5 times 4 times 3 times 2 times 1. But it can also be written as 5 times 4 factorial or 5 times 4 times 3 factorial. And the reason that it can be written shortened like that is in case you have, when working with the division of factorials, if your denominator has whatever the highest number that your denominator has in common with your numerator, you can stop at that number. So I'm going to show you an example because I know that may sound kind of weird without seeing it. Yeah, my little makeshift board just want to move everywhere in my makeshift eraser. All right, so I'm going to do an example before I do the examples they gave you. So if we had 5 factorial divided by 3 factorial, just like they kind of gave us, we will go, instead of going 5, we can go 5 times 4 times 3 times 2 times 1, which is what we know to do, and 3 times 2 times 1. But let me show you something. We know they both have a 1 in common, so those cancel out to 1 and 1. They have a 2 in common, those cancel out to 1 and 1. They have a 3 in common, which can cancel out to 1 and 1, and that simply leaves us with 5 times 4, which is 20. So now that's the way that you can do it. You can call it the long way, but it's still the right way. But now you can also go 5 factorial over 3 factorial, and to go 5 times 4 times 3 factorial, and we're going to stop at 3 because, like I said, the bottom's largest number is 3 factorial. We know that 3 factorial, both of those contain the same numbers. So we lock those out or omit them and have 1 and 1, our answer is still 20. So the answer does not change. Actually writing it like that is just a shorter or a simpler method. If anybody has any questions, I'm going to give you a moment to go ahead and ask, because we have 2 examples here that I actually want you to try. If you're on here, if you're not, I understand. But I'm still going to give you a minute. I'm going to run it like we always run it. So we have 8 factorial. Just need to simplify for that. And 12 factorial over 10 factorial. Okay, so let's do 8. Hold on. Oh, okay. Okay, so let's do an example of the 8 factorial. So 8 factorial, like I told you, is just taking the number that you have, and you're going to just descend. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And an equal sign. Hold on, let me get my calculator. I know I can multiply. Well, let me make sure I get my calculator out. So now my calculator, I'm going to simply just do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And our answer for this problem should be 40,320. And that's just descending from the number that we gave. So let me give you another example that's not on here for this type, but let's just say we had 11 factorial. It'd be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So on your calculator, you would just multiply 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that would be a bigger number, which is 399,168,000, which is 39,916,800. So the reason why I'm showing you these examples and also giving you the answer is because if you need to put it in your calculator to see that that is correct, make sure you do so. But remember, with the fundamental counting principle, sorry about that. My phone is crazy. So with the fundamental counting principle, you're going to always multiply between each number. We know that whatever the number is, that represents n, and then you descend to 1. All right, so let's look at this other example that we're looking at. 12 factorial over 10 factorial. Sorry about that. So you always count, yeah, like depending on. Okay, so if you had the number 7, it'll start at 7. So it's 7 times 6 times 5 times 4 times 3 times 2 times 1. Yes. So if, like I said, you start with the number that's given all the way down to 1. So in this case, the simple way to do this, which is your 12 factorial over 10 factorial, remember, the number that 12 and 10, the largest number they have in common, is going to be 10 factorial. So we can do the numerator, the numerator, yes. 12 times 11 times 10 factorial over 10 factorial. Because remember, 10 is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 anyway for both 10s. So that means these cancel out to be 1 and 1. So 12 times 11 is going to be, is that 132? Yep, 132. And that is the answer for both of the ones we just had. See how many slides we get. Okay, so we're halfway through the lesson. Any questions on these two before I push forward? Okay. So now we're going to talk about permutations. Permutations are different. Everybody is pretty much used to combinations of things, but permutations are similar, but they have a distinct position. So an arrangement of a distinct object in a specific order is called a permutation of objects, meaning it has a specific order. It has a specific role. That means if you work at a job and you're the manager. You're not just an employee. If you're the basketball coach, you're not the coach. You're the coach, you're not a player. If you're on the team and you're the captain, you're not just a regular player, you are a captain. You can also work with positions on a team. Meaning if you have a baseball team, you have a pitcher, you have a catcher, you have a baseman, I think they shortstop, or just different positions like that. That means you're good at what you're good at. You have a distinct position or a distinct order, and that is a permutation. So the number of permutations of n objects using all of the objects is going to be n factorial. So for our first example, it says in 7 of 10 years from 1998 to 2007, the 5 Major League Baseball teams in the American League East Division finished in the same exact order. That order is New York, Boston, Toronto, Baltimore, and Tampa Bay. Just how unusual is this? So find the number of possible finishing orders for these 5 teams. Now remember, they gave us 5 teams. They told us they came in the same exact order. All we are trying to do is leave them in that order, but figure out how many ways or how many possible orders can happen out of that 5 teams. So I know you probably saying, well, there's only one, but not necessarily. So first things first, we can draw this one out, actually. Remember, we had 5 teams. Of those 5 teams, well, we didn't have, it was more than 5 teams. Let's make sure we understand that. But 5 finished, the first 5 or the top 5 finished in the same exact order. So we know that the first spot, okay, well, let me do this first. We got New York, Boston, Toronto, Baltimore, and Tampa Bay. So in this first spot, just like before, it could be any of those 5 teams, because the way we know they came in the same order, but the way that we're trying to look at it is if it's a person off the street that doesn't know that it's going to happen that same way again. So if we don't know it's going to happen that same way again, then we know that there are 5 possible teams that can go here. But because they said New York was the first one, then New York leaves. The second one, we only have 4 spots. Now you see what's happening? Just like the factorial, Boston. Now Boston is gone. Third one, Toronto. And that was out of 3. Now we have 2 left, which is going to be Baltimore. Now they're gone. And for the last 1 slot, we have Tampa Bay. So now we're left with 5 times 4 times 3 times 2 times 1, which should be 120. There are 120 ways that those teams can be arranged, with those 5 being in the first 5 positions. Any questions about that one? Okay. So our next example says, how many different ways can a pledge class with 20 members choose a president, vice president, and Greek council representative? No pledge can have 2 offices. So that means that if you had 20 people, out of 20 people, there are 3 positions: president, vice president, and Greek council. Everybody else that's not one of those 3 are just going to be normal members. So in this case, because they only care about those 3 positions, we only worry about 3 positions. Trying to make it focus. I'm sorry. Y'all know my poor phone. Oh. All right. So remember, we have a president, vice president, and a Greek council. With those 3 positions out of 20 people, that means they told us it's out of 20. So in that first position, anybody out of all 20 can be the president. So when the president is gone, that means out of the rest of the 19, anybody can be the vice president. Then we also know, since that's gone, out of all of the rest that are left, which are 18 people, someone has to be the Greek council. So now with something this simple, we just stopped there because we only cared about the first 3 positions. So we have 20 times 19 times 18. And our answer is 6,840. Now, let me add something here. Now, if they wanted to know about the other members, what would make this a little bit more simpler is the fact that we know that, hey, that's 17 more people that are left. And of those 17 regular members, those cancel out to be 1 and 1, like if we were doing something bigger. So the only thing we were worried about were the top 3 positions: president, vice president, and Greek council. and there are 6,840 different ways that we can have those 3 positions out of 20 people. Do we have any questions? All right. So now, so you don't have to do things like this by hand, remember? We're going to get the equation. Our equation for permutation is going to include the P for permutation, which is NPR is equal to N factorial over N minus R factorial. So permutations of N objects taking R at a time. The arrangement of the N objects in specific order using R of those objects is called a permutation of N objects taking R at a time. It is written as NPR. Now remember, N is the total number of anything that you are working with. And R is going to be the specific space that is available for that. N is the total number. Just like before, we had a total number of 20 people, and the amount of spaces we had available was 3 for the president, vice president, and Greek council. So it's written as NPR equals to N factorial over N minus R factorial. Typically, we have to find N and find R and then use substitution into our equation or formula. All right, so here it says how many 5-digit zip codes are there with no repeated digits? Okay, so the first thing, let's do NPR is equal to N factorial over N minus R factorial. So it asked, how many 5-digit codes are there with no repeated digits? The first thing we have to make sure that we know is how many single digits are actually in our number line. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 total digits, which is our N, and they told us in a 5-digit zip code. So we have a 5-digit zip code. R is now 5. R is how many spaces in a zip code, and 10 is the amount of digits that we have totally in our number line that are single. So now I use a single process of the first things first, substitution. So now we have 10 factorial over 10 minus R. 10 minus 5 factorial. We're leaving that factorial on the outside because we need to solve on the inside of the parentheses first. So now we have 10 factorial over 5 factorial. So the first step is substitution. Second step from this point is simplify. And when we simplify, hold on. Yeah. I don't know if it's not letting you comment on the live, just I guess inbox me and I can answer your questions. I don't know why it's doing that. I'm sorry. All right, so here, when we simplify this next, so we simplified it after we did how about I say this? I'm not going to say simplify here. We're going to say, do your order of operations. To an extent, that is simplify. Now, our third step is going to be the breakdown. So we have substitution, simplify, and now the breakdown. We can do 10 times 9 times 8 times 7 times 6 times 5 factorial. All over 5 factorial. Remember, both of the 5s cancel out to 1 and 1. And so to find our answer, we have 10 times 9 times 8 times 7 times 6 times 1. And our answer is 30,240. Let's see if that's right. So like I said, these slides sometimes don't have as many steps as I do. So I know that they are good, but I also know that I try to make sure that I do the whole problem for you so that you can see the steps. As you see, the first step was just substituting the 10 and the 5. Remember, we got the 5 from being the amount of spaces in the zip code. We had the 10 because there are 10 total individual numbers in the number line. So first step was substitution. 10 factorial over 10 minus 5 factorial. Second step, simplify, which left us with 10 minus 5, which was 5 factorial. So we had 10 factorial over 5 factorial. In the breakdown, 10 times 9 times 8 times 7 times 6 times 5 factorial over 5 factorial. And both of the 5 factorials cancel out to 1. And we multiply what's left to get our answer of 30,240. Pretty much the same thing here, just without my steps to the side. All right, so the last thing that we have for our, the last thing we have for our section is going to be permutations. We're going to use the permutation rule with objects that are alike. So the number of permutations of n objects in which K1 objects are alike, K2 objects are alike, and etc. We're going to use n factorial over K1 factorial, K2 factorial, all the way to whatever you need to use. So in this case, we're going to have K1 plus K2 plus whatever all the way up to KP, which is going to equal to n. So let me explain that a little better. So let's say we're looking at a word. If we're looking at a word and the word has 5 letters, then that will be 5 factorial. Everything that's going to be at the bottom to represent K is going to be the type of letters. So if my name is Miss Adams, let's just use Adams, Adams, which is 5 letters. K1 will be A, which I have 2 of those. K2 would be D, which I have 1. K3 will be M, which is 1. And K4 will be S, which will be 1. So basically, everything at the bottom in the K area, the subscripts add up to equal to n, which is an n factorial. So I'm going to do an example. Okay. It says, how many different passwords can be made using all of the letters in the word Mississippi? First of all, let's count how many letters in Mississippi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means we have 11 factorial because the word Mississippi has 11 letters in it. So now we have the task of finding K1, which is M. They only have 1 M. K2, we have I. How many I's do we have? 1, 2, 3, 4. K3, we have S. We have 4 S's in the word Mississippi. And K4 is going to be P. And we have 2 P's in Mississippi. Sorry, so if we count this, that's 1 plus 4 plus 4 plus 2, which is 11. And remember, the word Mississippi has 11 letters, so that's why we have 11 factorial here. So now in that denominator for the K1, K2, K3, K4, we're going to have 1 factorial, which represents the M, 4 factorial, which represents the I, 4 factorial that represents the S, and 2 factorial, which represents the P. All we've done here is pretty much take the word Mississippi, which has 11 letters, and that's why it is 11 factorial in the numerator for N, the total amount that we're working with. And then at the bottom, we have our factorials on the letters that are in there and how many that are alike. So the categories are pretty much the alike letters in the word. So now with this one, remember, we're going to do it just as we did the ones from before. The largest number in the denominator is where we can stop from the numerator. So if I have 11 times 10 times 9 times 8 times 7 times 6 times 5, and I'm going to stop at 4 factorial because the largest number at the bottom that we have is 4 factorial. Those both are going to cancel out to be 1 and 1. So now what do you do with the rest of them? You do the same breakdown as you would do with them normally. We can just bring down this 1. That's 1 factorial. We have another 4 factorial that is 4 times 3 times 2 times 1 when broken down. And we still have that 2 left. 2 times 1. So just like we had 11 letters at the top, we're going to have the same amount of numbers equaling up at the bottom, even after we cancel. So you can either multiply this across and multiply the denominator across and divide, but I like to simplify. I know that 4 can go into 4 once, 4 can go into 8 twice. Make my number smaller. 3 can go into 3 once. 3 can go into 9 3 times. All I'm doing is making my number smaller. 2 can go into 2 once, and it can go into 10 5 times. 2 can go into 2 once, and it can also go into 6 3 times. So now if you notice, everything that I have at the bottom is a 1, so I don't have to worry about my denominator. But now at the top, I'm just going to multiply what I've simplified. 11 times 5 times 3 times 2 times 7 times 3 times 5. Now remember, like I told you, you don't have to simplify. You can go straight across in the numerator and denominator and then divide. Multiply the numerator, all of it. Multiply the denominator, all of it, and divide. But your answer is going to be 34,650. So there are 34,650 ways that we can actually arrange Mississippi with all these letters. All right, so as you see, we have now concluded 11.1. If you have any questions about 11.1, you can refer back to this video. It's here. You can watch it over and over again. I'm about to put it on Blackboard. You can watch it from there. Your homework, start working on it. Watch the videos from the homework. Have any questions, let me know ASAP. If you have any friends that you know that are in this class, please let them know. We are having class, and I know that it is after hours, but I wanted to put this video up in the evening so that if people can see it, they can see it. If they want to interact, they can interact. I don't know what people are doing in the daytime, but I know that a lot of people are in different places, so our times are not the same. You have any questions, email me, call me, text me, inbox me. If we need to do a one-on-one to get more clarification for you if you don't understand, send me an inbox and we can schedule a time. All right, so tomorrow, make sure for today you go ahead and answer your roll question. You'll have a roll question up for tomorrow, and more than likely sometime tomorrow I'll put up another video. For right now, midterm grades are due on Monday. I have reopened Chapter 8 and Chapter 9 test. Please take the test if you did not take it. If you did not take it, inbox me and I can send you the actual password for the test. I'm sorry, I'm looking in the days, but it's nighttime. Y'all have a good day, good night, be safe, stay in the house. Make sure y'all be careful out there. Have a good one. I guess.